we were discussing entanglement breaking channel. Okay, so we continue to discuss this, and our definition is following. So we have a map from, say, N from B of L of HA to L of HB, and is said to be entanglement breaking channel. We denote it by the entanglement breaking channel if one tensor N acting on any RA is separable state. Whether it is entangled or not, it's a separable state for all sets. So this is entanglement breaking channel. Then we prove the following. We proved N is entanglement breaking channel if that are associated Chai matrix, which is a state, of course, is separable. Chai matrix is a state in HA cross HA, HA cross HB. So, and it is separable. So, we have proved that. Okay. Now, we prove the following proposition. N from is entanglement breaking if and only if there exists Krauss operators for N, Krauss operators of rank 1. There exists rank 1 of rank 1. Rank 1 for N. That is, there exists K I equal to some phi I. This is how something will rank 1 operators will look like, and n of x equal to summation I equal to 1 to R. R will be the rank or whatever. This is it. I mean, depending upon whether they are in. So such that Ki x Ki star. Okay. This is how it looks like. Okay. So there exists, it just says it is entanglement breaking channel if and only if the Krauss operators, there exists Krauss operators. You can have different Krauss operators. There exists Krauss operators with rank 1. Okay, that's what this is. So proof. So if there exists Krauss operator with rank 1, okay, then Ki equal to the same thing. Okay, Pi. Okay, and I equal to 1 to R. Okay, then we know that N will look like that. Okay, 1 tensor such that N of x summation Kix Ki star 1 to R. Okay. Now we want to show that it is entanglement breaking. So let's take rho RA. So if maybe I forgot to say this RA, rho RA is in L of HR tensor HA. Okay. So rho RA in HR L of HA. A state, of course. Then we have to show that 1 tensor N of this is separable. So 1 tensor N. Okay. Now Ki's are rank 1 operators. 1 tensor N of rho RA. Now this is more or less same as what we did in the proof of this. Proof of this, more or less same. Let's see. So we just compute this. So we know this Krauss operators are given by this, and we know that Ki star with summation Ki star Ki equal to 1 because it's trace preserving. It's a channel, so that has to be 1. Okay. So we have two, these are all not need not be unit vectors. These are all just cross operators. If, I mean, for state, if you have state, then it will look like phi with phi equal to norm 1, be phi with norm 1. But here it's some operator. So there is no need, they are state operator. But you can have a constant here and you can make one of them normalized, one of them with norm 1. Okay. So okay, let's come to that. Let me make that assumption later. Okay. So let one tens are n equal to, so okay, let me write this with norm pi equal to 1 for all n. We can make sure we can take the constant to the other side and we can do this. So 1 tens are n of rho ra equal to, we have to apply this ka star, which is the summation over I equal to 1 to r. So ki, which is just phi and xi I, then rho ra, then again xi I, and phi, right? That's all. Okay, we have got this. So we have to show that this is a separable state. Okay. No, sorry. It is 1 tens are n, no. So I'll write that. It's not this. This is ni, this is 1 tens are n. Equal to 1 tens are n of that, which will be 1 tens are that, what do we have? Pi. Okay. Then 1 tens are phi xi, right? Pi. Okay. Then rho a, which has factors in the both the place, but this is 1 tensor. 1 tensor. Now this is phi. This is this way, right? This is phi xi pi. Okay, correct. This is the summation, where the sum is equal to I equal to 1 to r. I have just substituted this 1 tensor this 1 tensor this. That's what I have done. I mean, this is 1 tensor. Earlier, without tensor, I wrote. Okay. Now notice that this is, even though this is a multiple state, this you can write it as 1 tensor this, 1 tensor this. These are all, anyway, you can consider this as operator. Even though they are vectors, you can consider them as operator from C to whatever the dimension. From the, I mean, this like a linear functional. So you can, this will go here, and you will get that summation I equal to 1 to r. Okay, one tensor this phi I. Okay, and then something you have that. I mean, 1 tensor this, you are acting on this. If you notice one thing, this rho RA is a matrix on this, I mean, matrix with the operators coming from HA, right? These Xi's are in HA, right? Xi's are in HA. Xi's are in HA, and Phi's are in the range space, HB, right? When it is like this, this is Xi is in HA, okay? And Phi are in HB. Okay? That's how it takes an operator in HA. You get, it takes the inner product and you get a vector in the HB. So this is in HA, this is in HB. So this is in HA. Okay, HA. So these are all matrices. Rho RA is a matrices of I mean of the dimension, matrices of dimension R with entries coming from A, HA, with the entries coming from operator in HA. So when you hit it with these two things, it will just hit with each entry, matrix entry. It will just hit with each matrix entry. So when you apply this 1 tensor, that will leave it invariant. Okay, this one only will act on that. This will not have anything. So you can take this on the other side. So what I'm saying is this is equal to summation I equal to 1 to r. Okay, then 1 tensor this I mean the other way, sorry, I rho RA tensor. Okay, it is this. Okay, times that will go there. 1 tensor Pi, Pi, Pi. I mean, if you write it, whatever I explained through matrices, so that's what I said. This is just a matrix of entries coming from A. So this is from A. Each entry will be, you will take the inner product with that. So that will become a matrices. That will become a matrices on R. When you have taken the inner product, you will just scalar. You will get scalar. Each entry is an operator on this. When this Xia acts on that, you will get that's a linear functional. So you will get a matrix entry. You will get a scalar. So this is just a matrix on RA, which will commute with this. Okay, now this is clear. It will commute with this. So you can take it to the other side. So this is something which commute with this entry. Okay, and it is precisely this entry when you hit it with this. Okay, so because of that, it will go on the other side, and that's what I have written. So now we have got something here. Now you can see that yeah. Yeah. Now you have this. This is a state. This is as we have already seen. This is just a which is just a matrix on R basically, which is a scalar entry. So this is just an operator on this row RE. Okay, this is just a, and this is on this. So this is already separable. I mean, this is already product state. This tensor this, whatever you get here. And that is precisely, if you just take it, this is just going to take the, yeah. So, I mean, all I am saying is this is just a state on R. This is a state on R, and it is just the tensor product with this. Okay, that is clear, no? So that's because you have rho RA and you are hitting with this is, I mean, as I already said, okay, this is just if you are hitting with these things, you get a scalar operator. I mean, a matrix of dimension R with scalar entries. So it is precisely an operator on R. Okay. We have that there is no scalar nation equal to 1 to R. Okay. So I need some notation. Sigma I on that is R A okay, some scalar Pi, because they are not states, so we have to get the scalar. Where a tau I is the tau I is like it. Tau I is same as that. I don't need a specific notation for Phi. We have got it normalized. Norm Phi equal to 1. So this is a state. State since norm Pi. We have assumed norm Pi equal to 1. Okay. So and we have got where sigma IR equal to this rho one tensor, okay, which is an operator on which is an operator, yeah, on R, HR, okay, divided by trace of same trace of, okay, and that trace is what is called divided by Pi. Pi equal to that divided by Pi, that Pi comes here, okay, that is equal to trace of this one tensor, this chi I rho RA, okay, and then one tensor. Okay. Now you want to take trace. Trace is trace tensor trace. You can take the trace of, I mean, this is same as one tensor. Yeah, it is same as trace of one tensor. You take the first one. I mean, you take the partial trace on R. You get an operator on A. I mean, you want to take the trace of whole thing. Okay. So this is just rho A. Rho A is the partial trace of rho RA with respect to R. If you take the partial trace of R, then you get rho A. Okay. Rho RA times this, same thing. Okay. This is Pi. So now we have got a state. This is a state by this definition because you are taking something and dividing by the trace, and it is positive. Okay, I mean this is positive, but when everything action is positive, so this is positive. This is, I mean, these are all positive operators. Okay, so you get something positive divided by the trace, so you get a state here. You have a state here. All you have to prove is summation pi equal to 1. That's the only thing. Okay. Now we have that we have to use this condition. K star equal to 1. Okay. Summation I star ki, okay, which is just our I mean norm phi equal to 1. So this will just imply that summation I equal to 1 to r. These operators come to 1. This one is operator 1. So that is equal to 1. Okay. We have that. So now from this we get this summation pi equal to trace of this of summation I equal to 1 to r, I equal to 1 to r, trace of 1 tensor ki rho r a, rho, I mean rho a, can take rho a, okay, rho a, yeah, ki. You don't need the tensor, you can take, remove the tensor. Ki rho a, so that's what I want to write. I mean, it is just the, you take the partial trace, because trace is trace, tensor trace, and because of that. Now this is just trace of, you take the, I mean, you can, because it's trace, you can take it that side, rho a, summation I equal to 1 to r, ki. Okay, and this sums to 1. So this is just trace of rho a, which is a state, so it's 1. So we have proved one way, which is a state. So we have proved this. Okay. Now suppose in this entanglement breaking channel, you have to get a cross operator, set of cross operators of rank 1. Okay, that's it. That's clear, no? So we want to prove the other. Okay. So suppose this is entanglement breaking, then we want to get okay. So what do we have? We were the one, if it is entanglement, channel is entanglement breaking, if and only if the Choi matrix is separable. So that's the only condition we have. Okay, so let's just use it. So let the Choi matrix, which is in AB, I mean HA cross HV is an operator on HA cross HV, is a state on that. Okay, let this is equal to, so Choi matrix is separable. So any separable will look like this, Pi of product state. I mean, summation Pi, I equal to 1 to R of product state, maybe N or something, L or whatever, N, okay? N, summation Pi. Some product state you should get. That product, I mean, any state is a positive operator, and I mean, it's any state is a process which can be decomposed as a linear combination of pure state by spectral theorem. And those lambda is because of trace 1, because those lambda will sum to 1. So you can actually write it as summation Pi pure state. Okay? So that is just ki, tensor Pi. You can write it like this. Okay. So because it's a separable state. Okay. Separable mixed state, and that will look like this, where summation Pi equal to 1. Okay. Okay. That is that. Okay. Okay. Now we have to get a set of cross operators from this of rank 1. Of course, that's what we want to get. Okay. So we have to show it's a set of cross operators. Okay. Let's I think. Okay. How will we get? So the information we have is we have only the chai. From the chai matrix, we want to write this down. Write this down. I mean, getting the cross operator means we want to write it down. Okay, I can directly specify the cross operator, copy it from there and there. But let's just do that. Okay. So we have the chai matrix. Chai matrix is written like this. Okay? From this, we want to guess those operators. And for that, how we will write this. Okay? Enough. So it is determined by this, right? Any operators, anything at least determined on its action on the matrix. Then it's just a linear combinator. N of ij. Okay. So that is equal to summation I and j. Okay. I and j. So this is how we'll get, right? I terms are 1 of p, okay, times 1 j terms are summation over ij, right? I and j are matrix units for A, right? This is A. For any ij. Oh, sorry. Wait. Wait. No, I and j is not. This is just this. Sorry. Right? It is just this. Then let's just compute. What is phi? What is this phi? Phi is just some n acting on summation ij, no, ij tensor ij, right? One tensor in acting on this. Okay? So if you hit it with that I and j, you will get that I and you get the corresponding phi of ij. So yeah, there's no summation. Good, correct. Yeah, there is no summation. Yeah, it is this. Of course, that doesn't make sense. Okay, summation. So it is just this. Okay. Yeah. Yeah, we just want to determine that. So now let's write it. Now we know what is phi. So what is this chi matrix? So this is equal to I tensor 1. Okay. The chi matrix is, we just have to write the chi matrix here, which is just chi. Okay. Tensor pi, pi. Here the summation. This I is different. So let me change this. Change this to L or something. Yeah. The chi matrix is written like this. This could be something. So let me call it L. This is the summation. So L equal to 1. The I and j are fixed here. Okay. And this should be L. Okay. Here there is a summation. L equal to 1 to n or something, whatever, n or whatever. Okay. Then we have this j tensor 1. Okay. Okay. So this will combine together, ij. But we want to get, we want to get a chi matrix, not, we have to get rid of the tensor. We want to get the chi matrix. So I write it like this, summation L equal to 1 to n, okay, I, then chi L, okay, tensor 1, okay, then, so this is a scalar here. Okay, this is a scalar. So this tensor is just whatever the tensor here. There is no other tensor. And here this is going to be one tensor. One tensor. Mm, yeah, so now the whole thing will be scalar only. Okay? This is, I mean, goes with this. This goes with this, right? So we have J here, which is just IL J, okay? IL J, tensor this, whatever. I with IL, okay? This becomes scalar. Tensor this PL, okay? This is okay. And then IL J, J, PL. This is okay. This PL here, just come here, and this KL, sorry, yeah, this PL has come here and I have written here. This PL I have written here, okay, and this there's a J somewhere missing. I'm sorry. There's a J tensor one. No, there's a, after this there's a J tensor one. There is a J tensor one which I have missed. Okay. Now this KLJ I have written here. Right. That's what we have here. Oh no, I have written it. It's here. It's here. I tensor 1, J tensor 1. J tensor 1 is here. I tensor 1 is here. Whatever phi I have written here. Okay. P is just this, right? PL tensor, yeah. P is just this. Okay. Among this, I have taken KL J here. Okay, this is J. J here. Okay. And tensor this phi L. And similarly, that is this is scalar. Okay. This scalar you can attach with this. Okay. This is a scalar, and this scalar you can attach with this. Okay. So what we get is, and this scalar you can attach with this, and then you can write it as the bar of chi Li. What I am saying is this is equal to this number. That is here I bar. I mean chi L bar I. Yeah. Times here. Okay. And then the same thing. I mean, this scalar you can take it inside. This is a vector. If this is a scalar, you can take it inside. And similarly, you have this, the ket vector of whatever we have here. The same thing. I mean, this is a scalar I'm writing here. Scalar is inside. Okay? This is just chi L J. Okay? J bar of this. This is chi L. I mean, this is the inner product bar of that times PL. Okay? PL. Okay. Now all we have to worry about only this. It is just the ket vector of this. It is just the star of that. Okay. So if you define and summation over L equal to 1. Okay. So define KL, okay, KL acting on I to be just this. KL acting on I to be just this. I mean, it is just this, which is just PL K. You don't need you can just write KL equal to PL dial bar. It's a rank 1 operator. PL KL bar. Its action on I is precisely this. Okay? And that is the ket vector of this. So this thing becomes This is equal to summation L equal to 1 to N KL, whatever you have, KL of I, J, KL star. So we have got Krauss operators like that. Okay. So these are Krauss operators. We have to verify that summation KL star. Have we verified that? So that should have something. That should be PI somewhere, no? I'm sorry. Wait. Wait. There are some scalars missing. So here there should be a square root of dA should be there, because you will get gamma tensor gamma. So you will get a square root of dA has to be there in this formula. So there is a square root of dA everywhere missing. Square root of dA, square root of dA everywhere missing. Okay. And there is some, this PI should come somewhere, no? The Chai matrix has a PI. So there should be a PI. So not square root of dA. dA is missing. dA, not square root of dA. dA is missing. So with this thing, there is a PI, no? There is a PA coming with the Chai matrix, right? We are using that PL. There should be a PL here, no? Summation over PL. So there should be a PL here. I'm sorry, I missed this scalar. There is a DA and there is a PL inside. Okay? Only here I'm including. There is a PL inside. There is a DA and there is a PL inside. And there is a DA and a PL inside. Okay? So DA. So DA and PL inside. So we have to take KL to be square root of DA PL. Okay? You have to take it like this. So now we have to consider this KL star KL. Okay? That is equal to so DA, where will DA will get cancelled? KL star KL and summation. I mean, if you take this star this first summation KL, let's just write it. This is equal to summation DA PL. Okay, this star this star will be PL bar times PL PL, right? PL is 1. Okay, so we don't worry about this. We just have KL bar only. KL bar this way, sorry. Bar. Okay. And okay. Summation PL equal to 1. So PL equal to 1. And why does that sum to 1? Yeah, summation KL. I mean, these are KL is coming from, I mean, Ka is in A operator. That will sum to its dimension. Okay. I mean, right? That will that sum to, it will sum to dimension because of, yeah, trace of Ka is, I mean, that is the Chai matrix, no? See, this is given by this. So, PL. Chai matrix has, I mean, if you take the partial trace of this, the Chai matrix, it is just the partial. If you take the partial trace with respect to this, then you get this. Okay, that will be identity divided by dA, right? So summation KL will be summation PL KL will be, yeah, summation PL this KL. I mean, you have bar, you can cancel both the bars, and this is equal to 1 divided by d. 1 is the operator d. Because if you take the partial trace of the Chai matrix with respect to one of them, with respect to the B of B HB, then you get this operator 1 a divided by this, which we have noticed, okay? Which you have used in the last one. Because of that, this is equal to 1. So that should be equal to 1. I'm sorry for the mess. See. Okay. Yeah. Okay. So this is done. We are done, no? Yeah. This is a rank 1 Krauss operators. It's trace preserving. We have to verify that summation KL star KL equal to 1. And we have verified that it evaluates that operator. And we are done. So what is next? So examples. We have for example, we have defined two channels which are called classical quantum channel, quantum classical channels. And we have explicitly wrote down the Krauss operators for them. And they are rank 1 operators, if you remember. They are rank 1 operators. They come from the spectral decomposition of the corresponding. I mean, classical quantum channel is something which takes a vector xx to some sigma x. And that sigma x is a spectral decomposition. And using that, we wrote the Krauss operators up there. Okay, so they are all rank 1 Krauss operators. They have rank 1 Krauss operators, and also the quantum classical channel also rank 1 Krauss operators. So both are entanglement breaking channel. Both classical quantum channel, quantum classical channel, both are entanglement breaking channel because they have Krauss operators of rank 1, which we have already verified. Okay? I'm changing. Yeah. Okay. So the classical quantum channel looks like this. Quantum channel, which takes these operators xx x prime, delta x prime times sigma x. Okay? And this is a entanglement breaking channel. And quantum classical channel is something which takes any rho to trace of rho mx times this. Okay? So this is also entanglement breaking channel because they have rank 1 Krauss operators. Okay? So if you compose, so the composition of two entanglement breaking channel is again entanglement breaking channel. We noticed in the last class. So because of that, composition is also entanglement breaking channel. So any operator rho going to summation trace, I mean where this summation mx are positive, summation mx equal to 1. That's what is called a POVM, positive operator valued measurement. Okay, that is what this mx is given by. So rho going to trace x rho times sigma x. We just compose those two things. Okay, where x is in some set. Okay. This is a channel. This is a composition of classical quantum channel and quantum classical channel, or quantum classical channel and classical quantum channel. Yeah, the other way. First one is quantum classical and then classical quantum. So you get a quantum channel. Okay, you get this. So this is the composition. So this is an entanglement breaking channel. This channel, rho going to this is an entanglement. We want to prove every entanglement breaking channel looks like this. Okay. N from L of H to L of H E is entanglement breaking channel if and only if there exists POV mx such that n of rho equal to summation over xn. This is an xn some set. Space of mx rho sigma x. Okay, for some sigma x, and all that. There exists and sigma x should be in, of course, state in L of HP, right? L of HP, and mx should be there. Mx should be in HA. So this is what you want. Okay. So we are assuming we have already proved any such thing is entanglement breaking channel. We have to prove the other way. So N is entanglement breaking channel. Okay. Now we want to prove that it looks like this. We want to get this. Okay. So there exists Kx equal to the x, maybe whatever, doesn't matter, Px, okay, such that n rho equal to summation plus Kx star and summation Kx star Kx equal to 1. Okay. So we assume, without reality, assume norm Px equal to 1. Okay. This implies summation. I don't know whether we need. This is something we have already done, so I'm just using it. Okay. Let's see whether we need it. And so we have this. Okay. Now we have to get. So we have a phi x and xi x. Okay. Now we have to get positive operators mx. Okay, let's write it. I mean, we should guess from this phi x should be in A, right? And this should be in B, right? I mean, then only it will take anything, any row, and it will hit it with this. You will get a scalar, and you will get something in B. Okay. Okay. So we have to guess at the mx, and I mean, it's clear, no? Mx has to be, it is this, Zx, right? Mx is this. We want to have, yeah, Zx. We don't need it to be a state. Okay. And we have this condition, right? Yeah. We don't need it to be a state. We only have this condition. This is not unit vector, but this adds up to 1. So this implies we already have summation mx equals 1. We already have it. And the other one should be state. So the other one should be state. And we want to get sigma x. Sigma x is this, which is a state. Then, of course, n of any row is equal to, we can calculate the trace of mx row equal to trace of row, which is just, you can bring it here, which is just row, let's say, right, which is just this. Okay. And n of row equal to, and that's what we have. I mean, n of row equal to, you have to use the curves operators, x such that xi x. I'm sorry. I think it's the other way, right? Is it right? We get something in B. Sigma x is, yeah, I think I have written it correctly. But here, no. I mean, this is A, that is B. Here I have written it in the other way. This will be in B, this will be in A. Okay, so Vx is in A. So we have to get. So we have to get. I mean, this Mx should be in A, no? So we have to have Vx here. Then it will not add up one, no? Then we have the other way. We take X to be. Wait. Let's see what we need. Okay. Yeah. I mean, this X should be in A, right? Which should be in A. This should be in B. This should be in A, right? Or we should have, sorry. This is Px, right? This should be our Mx. No, our Mx cannot. Mx should be in A. So this is. Sorry. Okay. So here we have to change. I'm sorry. Here we have the condition. Kx will look like this. N of rho equal to Kx rho Kx star. Kx rho Kx star. N of rho will be like this. And Kx will look like X Px. I have assumed that norm phi equal to 1. Instead, I can assume norm X equal to 1. Okay. Then this will sum to 1, right? I mean, we can take one of them to be norm 1, then the other one will sum to this. Is it right? No, it's not correct, no? Px star, that will be Kx star will be, Px will come here, Px will come here. Yeah, that's right. That's right. This is the right thing. This is the right thing. The summation Px is 1. That's right. If you take it star, Px will come as a vector here, and this will become a linear functional, and that will add up to that. I mean, they are norm 1. That is just inner product, right? This will become like this. That will be inner product between them, and the Px will add up to 1. So this is okay. I'm getting too much confused. Okay. So now let's change one by one. So phi x, which is right. Then sigma x is equal to sigma x should be x. This is a vector in B. Okay. This is in B. Okay. This is in B. N of rho equal to x B Px rho Px Zx, right? Zx. Now this is just mx is where is it? Mx is Px, so this should be Px. Okay, mx is Px, so this is Px. Okay. Now this is what you have here, which is the trace here. Okay, and you have psi x, which will add up to. I mean, this is just the kx star. What do you want to get? You want to write, and this is just equal to summation base of mx rho times sigma x. This is just in this form. I mean, it's very easy. It just with all these things, it's getting confused. You can write it down. Okay. So this is about entanglement, and we want to get something about complement of entanglement breaking channel. We want to talk about something. This will break any entanglement. So we want to talk about something a complement, which is a complement of something. That is what is called Hadamard channel. Okay, that's what we will define now, and prove that Hadamard. We will define Hadamard channel with respect to a basis and through something specifically as an operator. Then we will prove that it is actually a complement of entanglement breaking channel. It's if and only if thing. One way, other leave it as an exercise. It's just tracing back the same argument. Okay. So definition, Hadamard channel. So a n from L of HA to L of HB is said to be a Hadamard channel. You should notice that this is basis dependent. Okay. If there exists a n it should be in L of HB, n is greater than 1, and the diagonal with diagonal of n, each entry of diagonal entries are 1. Okay? With diagonal equal to 1, 1, 1, 1. The diagonal unit elements. Okay? With the unit diagonal elements, diagonal is just 1, 1, 1. It can have other things, n like this, such that this n of rho equal to, I will define what this star is, and there exists a isometry. There exists a n and an isometry V from HA to HB, such that it is a composition of an isometric channel and what is called a Schur channel. Okay, no, this is Hadamard channel. This is there is something called Schur product. N of rho equal to n star V rho V star, okay, where star is the Schur product. I will define what is this. It is just product-wise, point-wise product of matrices. Matrix multiplication is there, matrix multiplication. But you can multiply point-wise. Xij and Yij, you can multiply and form a new product. That's also a product. That is what is called a Schur product. Of course, that is not a homomorphism under matrix multiplication. It will not respect matrix multiplication. In some cases, it will respect. It will be surprising. That is what is your spin model will, if you have studied it, spin model will have that two thing. I don't know whether it is noted. I noted it long back, and Sundar was very surprised, but he never wrote it. But I think KSAB has done something on that. Okay. So it is a Schur product. That's something else, some other discussion. So Schur product is something like this: X star Y I J equal to just Xij Yij. That's all. Okay. X is a matrix, Y is a matrix, XY, X star Y at Ij is Xij Yij. You have to first verify it's a channel, and then I want to prove that this is actually a complement of this complement is entanglement breaking channel. Or you can prove that other way also. Okay, I will state that as an exercise. Okay. N and above can be defined through a matrix capital N and script N defined through capital N and an isometry defined above, which is we called as Hadamard channel. For the complement is an entanglement breaking channel. Channel, we will write it in the Stein spring form. That is, there exists an isometry. I mean, we are already given an isometry. Then we construct another isometry, and we so that we have a this channel is written as an isometric channel composed with a partial trace channel. Okay, so in the Stein spring. Okay, so let n of rho equal to n star b rho b star. Okay. So any positive matrix, n will look like some x star x, right? Where x star is just this this vector and this vector. I mean, this vector and its star is this. So this is a bra, which is ket vector, and this is a bra vector. So it will look like an inner product. Okay. So let is equal to n of nij equal to some yeah, right, okay, for some vectors. Okay, for some vectors like this. Okay, it will look like this. Correct? I mean, this is the ket vector. You are taking the bar and the transpose of it. Okay? So nij looks like this. Okay, then n of rho, first we have to compute this. Okay, so I mean, this, what is this matrix? This is for ij. Summation over ij, the matrix unit ij, and ijth entry. Okay? This is a matrix. This is n of rho is a matrix. It's ijth element, I write it, and then I write the matrix unit ij. Okay? So I write the matrix I, then I have to write the entry here. So that entry is going to be ijth entry of this, ijth entry of this. Ijth entry of, so I have to get the ijth entry of this. I mean V rho V star J. That's all. Right? That's all. Okay. Now you take this as vector and this as one vector. Okay. So V star, V is from HA to HB. Okay. E is from HA to HB, and V star is from HB to HI. So let EI. Now notice that these IIs are in HB. Okay, because that's a matrix in HB. So that's a matrix in HB. And that Phi is in HA. You should write it in the top. Is in HB. Sorry, HA into B. V star of V star of whatever, V star of I. I mean, here it is J, so V star of I. Okay. Now this is enough rho is going to be summation over I and J, I, J, and then it is just Pi, Pj, right? Pj, and then Ij. That's all, right? Okay. Now we can guess the Krauss operator from this. So this is, let's see what is this. This is in B, this is in A, just to make sure. And also, this should be in B. Okay? This should be in B. Okay? That is where, I mean, this is an element of B, so that should be in B. That is in B. Okay. Now we want to guess the Krauss operator. I mean, we want to prove the complement is entanglement breaking, so we have to guess the Krauss operator. No, before that, we want to guess the Stein spring. Sorry, we want to guess the Stein spring, and from that, we want to guess the Krauss operator for the complement, which we have to prove it's rank 1, then it is proved. That's what we have. Okay. So now we have to get the Stein spring. Okay. That will be like HA tensor HR, right? I mean, Stein spring means we have V from HA to H, we have already an isometry from which is embedded here. Okay, we don't care about it now. So we want an isometry from, so let's call, say U unitary, but here let's say just unitary. I mean, the isometry HA to some HA tensor HR. you can guess what is this R. We have these vectors chi1 up to chi r. That should be R. The space generated by chi1 up to chi r should be R. Okay, so we can have that U of yeah. What do we get? U of I. Let me just I. Then we have to take. I mean, we have to get rid of A. So we put tensor I. This will be in R. This will be in this. This will be in I. So these are all just I. Okay. Now I just sum over. Okay. I mean, wherever that summation is. Mm, there is one problem. Wait. This I, this phi, these two are different, no? Maybe some more I and J. Wait. Wait. No, the phi I's are in HA. And I and chi I, they are in HB. Okay. So possibly there is a summation over IJ. What are we supposed to get? Um, U. Wait, and my confusion is this phi I. This phi I's are no, that's okay. Phi I's are not orthonormal. Phi I's are indexed. I mean, what are these phi I? Phi I, where I define phi I? Phi I equal to V of I. So this is from B, right? So this is indexed by the same I. Okay? This is indexed with the same I. I varies over the dimension of HP. Phi I varies over that. Okay? Maybe they need not be linearly independent. There is no condition on that because that is it is a V star of that. So that will that's not an isometry. That's a co-isometry. That will not preserve anything. It is just a star of isometry, which will have kernel also, which may be even zero also. Doesn't matter. Okay? Which may take something to zero. Which can have kernel. So this is okay. That was my confusion. My confusion was this is in A. So how can I take with this? But this phi I mean, this is indexed by same phi I as I because V star of I we are only taking. So that's why this is okay. This is okay. Okay. Now let us just consider. I want to claim that this is an isometry. Okay. Now U star U equal to summation over I and J. Okay. Now star of this I have to take, but that will be this will become the other vector, bra vector, and that you will get a ket vector. That will I only when I and J are equal, they will be same. So we will get summation over only I. Okay. Then we have to take the other way. No, this is chi I. Let so. Hmm. So this is also, I mean, what is chi? Summation. Chi's are unit vectors. The diagonals are 1. Chi is 1. We have assumed that in the, definition of that capital N, it has diagonals unit diagonal. So they are all number 1. So this is 1. So this is just summation over I, just this, Pi, Pi. Okay. This is okay. So this is just summation over I, V star V. We get a V star, we get V, sorry, what do we get? Pi, Phi. Phi is, that is V star, right? So we get V star. I'm sorry, we get the other way. Phi will turn it the other way, no? It's this way. Yes, this is just this Pi. Okay. So this is 1 because the diagonal entries of N is 1. So this is 1. And this is over summation over I, Phi, Pi. Okay. We have an isometry there. The summation over I. V star of I, okay, I, V star. Okay. That's what we have. Summation over I, V star here. Summation over I, this is just the basis. Summation over I is 1. Summation over II is 1. So this is just V star V. Good. We have got it. Okay. So we have proved that U is an isometry. Okay. So U is an isometry. U is an isometry. We have proved it. Okay. So if you want to go through, I have just used the fact that this N has diagonal 1, and I have used that V is an isometry. These are the two ingredients that I have used here to prove that U is an isometry. So you have got the U is an isometry. Now we want to prove this is actually the Stein-Spring representation. That's because I have written this complement channel here and then this channel here. We have to get it. And okay. Now we want to, so now only we are proving that this N is a Hadamard channel is actually a channel. And we call it as Hadamard channel, actually a quantum channel. We are only proving now. Okay. So now we want to calculate N of rho. So N of rho, what is U rho U star? We will first compute this. U rho U star. U rho U star is summation over I, okay, I, Ei, okay, tensor I, rho I, and star of this, okay, which is right, star of this is Pi, Pi, okay, I, okay, correct, Pi, I, okay, tensor, that Chi will also become like this. This Chi will become like this, and that will become, no. You want to take, we want to take U rho U star. So direct, I should take direct straight, sorry. We are only looking at U rho U star, no, not U star. So I just have to write it directly. Summation over I, Pi, okay, tensor Chi, I'm sorry, rho. Now I have to write the flipped one. That's what I wrote, is it? What is that? This is to be Phi. This is flipped here, so Phi. Unfortunately, I don't have the physicist practice flipping this these things. Okay, this is right now. Okay, tensor, and I have to flip it. Right, correct? Is correct, no? Euro U star is this. I mean, whether I have flipped everything, I mean, this is just I have copied directly I have written. Then U star is this. Okay, summation over I and j. Okay, this would be j. Okay, I and j. Okay. Now, okay. So summation over I and j of this. Okay, now this is some row on this. Now this is a vector. This is in HR tensor HA. Okay. Now I take the trace over R. Trace R of U row U star. That's what you want to take. Okay, I want to get that Ni. If I take the trace on R, I think I should have written it differently. I have interchanged the R and I. I mean, this is R, this is I, actually. If you don't mind. Okay. I mean, usually we write it HR this way and then take the trace, but I have changed it. Doesn't matter. You just remember this, okay? This is okay, okay? So I take the trace R on the second one. Trace is the second one. Okay. This is equal to, we have to get that channel back. That's what we have to get. So we are tracing it out the first one. So, okay. And I mean, you will just get that, no? I mean, we will, there is one thing, chi j, chi I. There is one, so there is a mistake in the book also. I mean, this is a mistake in the book. We need bar here, right? Okay. That's what you will get here. You just look at it. We need bar here. Okay. If you take the trace of this, okay, you have a row. You have a row here, but row is, I mean, you see, row is in HA. Okay, row is in HA. Then by these two vectors, I mean, this is just a, this is, I mean, there is a vector from C to HR. Okay, where I haven't defined what is HR. HR equal to span of Zi. Okay. HA to SB, HB, correct. So this should be in HB, sorry. This is in HB. Chi I's are in HB, no? So what is in HB? I's are in HB, sorry. Chi I's are in HR. Wherever chi I is, doesn't matter. Chi I comes for this matrix. It can come from some other space also. Okay, but you can take it to be span of chi I to be this. Span of chi I could be a subspace of HB, or it could be some other space also. I mean, N looks like X star X, where this X could be anywhere. Doesn't matter. Okay, so you are taking that. It could be in HB itself. You take the span of chi I to be HR. So this should be HB, correct? I's are in HB. This is in HA. The I's are in HB. Okay, so we are taking trace R. Okay, trace R. And what will be trace R? I'm just saying that you will get, I mean, this will be just, that's what we have got, right? This will be this. This is just, I mean, you just look at it. Summation over. If you take these two, trace of this, trace is just the trace of, you are taking the trace on the second one, right? Second one. So, I mean, this row is in the first one. So row is in the, I'm just saying that this is just, let's write it and it will be clear. Okay. I'm just saying Phi row Pj. J, then that's what I will know. P8, what is it looking at? Ki, I, but we get Kij, Ki. We get Kij, Ki, no? It will go there. Kij, Ki, then I, J. Even though there is a tensor, that becomes scalar, right? If you take the trace, this will become a scalar and it comes like this. This is what you get. This is clear? This is clear, no? So that's what we have there. That is what we have here. N row is looks like this. Okay. Ki, Kij, and that's what precisely we have here. Except that we will get bar of this. I mean, we get Kij, Ki bar. So I'm sorry. I want to get sorry. I want to take bar here. I want to take bar here. If you take bar here, it will. If you take bar here, then you will get bar here, and you will get finally you don't get bar. Okay. Yeah, you need a bar there. It's a mistake in the book also. So we have got this. We have proved that N is a channel and its time spring percentage is given by this. So we have to only take the other trace and get the complement channel. Okay. Now you take N complement. Okay, N complement equal to trace R of this Euro U star. Okay, Euro U star. That's the complement channel, right? Huh? Sorry. Trace with B. Trace with B. Sorry. Yeah, trace with B. Okay. So now if you take the trace with B, okay. So trace with B. So Euro U star looks like this. Okay. Euro U star looks like this. If you take the trace with B, this, I mean, you have this I and j will go. It will be just summation over I. Okay. This will be summation over I. Okay. Summation over I, and yeah, summation over I, and summation over rho. Yeah. Pi, Pj with that's right, no? Rho Pi, Pj. Tensor. This is a scalar, right? Tensor with Ki bar Ki. Okay, that's what we have. So this you can write it as summation over I. Okay. Ki bar Pi. K bar phi, okay, rho with, and then the same thing, right? Pi, Ki, summation of it. So this is a Kraut operator that Ki equal to Ki bar. Then N complement equal to summation Ki rho Ki star. So rank of Ki equal to 1. So it's an entanglement breaking channel. Okay. So if you have a Hadamard channel, so we have proved it's a Hadamard channel. Hadamard channel is a quantum channel. We have proved it by time-spring, by explicitly writing the time-spring representation. We consider the complement one, and that gives that's with Krauss operators of rank 1. So it is entanglement breaking. That's all. So we have done. Maybe summation Ki, that follows because you're getting it by tracing out from an isometric channel. So it will be a channel. You don't have to worry. I mean, it will be there. So it's ensured in that. So we are done. Good. stop here.